that we can start now. Okay, so welcome back again and hello everyone. So I'm Pierre Bonnen and I will be one of the speakers today for the last webinar of Pyleecan. So today the webinar will be more about how to contribute to Pyleecan. So we will explain you everything about how to contribute, what is GitHub, how to create some classes in Pyleecan and so on. So as a speaker today, so I will do the first part about how to contribute to the topology and the slots, for instance. Then there will be Emile de Villers that will explain to you how to contribute to the models. And finally, Hélène Toubin will explain you a bit further how to use SciDataTool object. So again, we thank the University of Casino and EYT for co-hosting this webinar with Greenforge Club. So this webinar is the third of three other webinars. The two first videos are already available online on the Pyleecan website.org if you go to /tutorials. Now that everyone is far away, I will remove my mask so you can understand me better. Okay, so this webinar will be quite different from the two previous ones. This one will be more about a great discussion and a great explanation of every single step that you need to do for contributing to Pyleecan. So there will be very few notebook usage, for instance, and we will share some global advices about how to contribute and what is the global structure of the project, so you can understand everything. The idea is that we will detail some concepts that are very general, that are not limited to Pyleecan. The idea is that some of the architecture choice and the way of contributing, for instance, are something that you can reuse even for some code that are not linked to Pyleecan. So that would be a quite general discussion. So as I said, I will start by explaining to you how to contribute, how to create a slot in Pyleecan. So actually today I will do a pull request. I will explain to you what it is later to add a new slot in Pyleecan. Then I will show you a very new feature that we have added this week that enables to import any shape as a DXF for slot and holes. And again, then we'll talk more about how everything is structured on the models so that you can reuse all the power of Pyleecan when you are developing your own. And finally, the SciDataTool objects, so you can benefit of everything that Hélène showed you last week. So let's start by going to the GitHub of Pyleecan. So if you go to github.com/eomi/Pyleecan, you have the core and the beating heart of Pyleecan project. Everything is gathered here. So every time you need to interact with the project, that's where you need to go. So first, the first page that you will see is all about code. So that's quite straightforward. You can go into any folder and you can see what are the methods of any object in Pyleecan. So for instance, if I go here, I will see how we compute the surface of the slot 14. So the idea is that everything is available, so you can see, so you can look and play and start to go into detail in the code. I will explain later how all these folders are organized. So this is a very important page because you have everything detailed about the project, small presentation, the current version, the license, and so on. And the second page, which is very, very important, is the issue page. Basically, it details every discussion that we currently have within the community. So you can see what we are talking about and what will be the future of Pyleecan. For instance, you can see that we are currently talking about doing a coupling with Elmer, for instance. We have some idea of how to optimize how we handle mesh in the project, for instance, and some overcoupling that we can work on. So basically, every time you want to see what is currently happening in the project, you can go have a look on the issue page, so you can see what is currently happening. And every time you want to contribute to Pyleecan, the first step is always go to issue and open a new one. So for instance, you just have to click here, and then you can create your own issue, and you can start to talk with all the community and so on. So I won't create a new issue now, because when you want to contribute, the first thing always is to look inside the existing one, is no one is already working or thinking about the same thing. So something that you can do, for instance, is you can use the labels, so you can filter and see what is currently going on. For instance, if you filter on help wanted, you will see where we are looking for contributors for Pyleecan. This is quite a very important label to filter on. For instance, you see that we are working currently on the gmsh page. We are always looking for validation cases. So if you have a publication or some experimental data or a way of proving that the models in Pyleecan are correct, please share it with us. That's very important. And some other global things, again, you will have to take a look to see what is what match what you are looking for. So in particular, here I say that I want to create a new slot, so I will filter more on topology. I will just remove the first label in the research. And something important is that there is also the is open. So if you remove that, you will see if the issue that you are wanting to create, someone maybe have opened it before. So you can also see what was the history of the project. So so again, I want to create a new slot, and here I see design of a double cage rotor for SAEM. So I click on it, and here is the schematics of a slot that a user of Pyleecan wants to add, so he can simulate a squirrel cage induction machine with double squirrel cage. So he had a very good first idea of opening an issue, so that we were able to discuss with him about what is the best way of adding the slot. So we share with him some resources, tutorial, we link it to some other pull requests. We discuss with him about what should be the schematics and so on. And at the end, we have created this schematics, which is more detailed about exactly what will be the slot. I will come back a bit later on this schematics, but if you are interested, you can go to this link, and you will have the schematics that could help you understand the code that I will present to you in a few minutes. So it's this issue. Okay, so now you know what you want to contribute to, because you have talked about it with the community. So now you need to get started. So the procedure that I will explain to you now is not completely, is not only for Pyleecan, it's the way that you can contribute to any open source project. That's a standard, and that's a good one. Maybe it can look complicated at the first time you will see, and I will explain it to you. But keep in mind that without all these tools and without all these constraints, it won't be possible to contribute on an open source project. Because we need to think that people are all around the world. They want to contribute on the same code, so they need to have a convenient way of sharing files and of sharing modification, and avoiding having somewhere in the world a folder with some files that everyone try to manipulate at the same time. That won't be possible. So the idea is that all the system that I present to you is a way of in a neat way of handling every modification on a project. So, as I show you, if you go on the main repository of the project, you will have all the code. So everything is here, but you won't be able to modify it, which is quite important because we don't want anyone to be able to change the code of Pyleecan. Maybe someone would want to change the result, so it may be wrong now. So it's a normal protection. So you will have to always ask for permission to modify Pyleecan. So the first thing you will have to do if you want to actually modify the code is get the code yourself. So the first thing you need to do on GitHub is create your own account. So you know who you are. So anyway, you will have to create your account if you want to open an issue. So we can discuss with you about how you can contribute. And then you click on fork. By clicking on fork, you are copying the project Pyleecan. So if you take a look here, now it's not eomis/Pyleecan, it's my name /Pyleecan. The idea is that this is a copy of the original project, but it's mine now. So I can do all the modifications that I want on this copy, and it won't affect anyone else. So that's very interesting. That way I can play with the code in its full potential, and I can do some very wide modification, and it won't break everything for anyone. So that's quite interesting, so we can contribute to. So you have no risk of harming anyone. You can do your modification on your side. So that's something very interesting. So now I have my the code within my GitHub account. So now I need to have it on my computer, so I can interact with it, because here it's not convenient to modify the code directly on GitHub. Actually, you can do it, but it's not the perfect way of doing it. So you can go here, and you have the link to clone the repository. So it will explain, so it will basically just the link to all the code that is presented here. So I will just copy it. And then if I go to my desktop, I can use a tool which is known as Git to get the code. So in particular, Git is a software that will enable you to get the code from GitHub and put it on your computer. And here the tool I'm using is Turquoise Git, which is a very convenient way of communicating and using Git on Windows. There's lots of other ways to use Git, so you can have a look on the internet to see some tutorials about how to do that. But here I will be using this one, which is very convenient and very simple. If it's your first experience with Git, you should start with it. So I will create a Pyleecan webinar folder on my desktop. So you can see that he is getting all the data and all the files that were on GitHub and copying it directly into my disk. Okay, so now that is starting to download, we'll start to go about what we are going to develop. We are going to develop a slot. So the first thing very important to know is what is a slot in Pyleecan. So we come back to the presentation. So a slot object in Pyleecan is an object. So I will do the same reminder as we did last week. So an object is basically a black box that you can interact with in a normalized way. So we have the properties that define the object. So in the example of my slot, it will be the dimension. So if you come back to the schematics, you will see that there are several heights to define and to draw it. So the property define what are the proportions of your slot. And then there is a method that enables to interact with it. For instance, what is the height of my slot, what is the surface of my slot, and so on. So again, the idea is that if I have two schematics like this one, you can see the properties that are defined on the slot. So on the one on the right, you have H0 and H2 that define the height. And so these are the property of this particular slot. The property of the other slot on the left are different. but the idea is that it doesn't matter. At the end, we put that in the slot boxes, and it doesn't matter what is inside. You just know that you can interact with it by calling comp height, and it will always return the height of the slot. So that's always the same principle. As long as an object exists in Pyleecan, you just need to know what are the methods that you need to develop. And as long as you develop them correctly, your object will automatically be available everywhere in Pyleecan. So again, object-oriented programming can look complicated, but at the end, it simplifies the way of developing new features greatly. So, and then again, we gather the classes by family. So classes are some global concepts, a lamination, a slot, a machine, and so on. So we have some classes that are abstract, so which has some global concept. So for instance, we have the slot class, which is fully abstract. You can't create a slot object. You always have to create what is named the daughter of the slot. So today I will be creating a new daughter of the slot class. So that's what we will be doing. So we will create a new daughter. And the idea is that I have some method in the slot class that can be called in any slot as long as they are a daughter of the slot class. And I will show you when we'll be creating the new slot, how we can have both ways. So we can get methods from slot and methods from your own object. So now let's go back to the slot. So as I said, here you have the slot abstract class. And then we have split the slot into family, the slot with winding and the slot with magnet. In fact, it's something that we think that we can do better because we realize that we can find a way of saying, okay, it's just a slot with an active surface within it. So it's an issue that is currently open on Pyleecan. The idea is that we want to merge both of these classes so that, for instance, the slot that I will define, if you want to say, okay, it's not a winding, it's a magnet, maybe one day in Pyleecan you will be able to do that. Does it make sense? I don't know, but you will be able to do it. The idea again is that we want to have some object that you can reuse in the more generical way. So you don't have to do the work twice, for instance. And so we separate the slots. So the slots are just a combination of lines that you draw on a bore radius of a lamination. And then we have the holes. So that's basically holes or pockets that you carve inside the lamination. So these are two very important class to understand and to know if you are going into modifying classes within Pyleecan. So then, so now you have the slot classes. Then on the top there is a lamination class. So when you have lamination with slot containing winding, lamination with slot containing magnets, lamination with holes, and so on. So you have again a great diversity of lamination objects. And at every time we change a new parameter, and we are able to define some new way of what exactly these laminations are and how they behave. So you can see a lamination with hole here and a lamination with slot here. And finally, the machine objects are just a combination of different lamination objects. So again, you just have to assemble your object in a convenient and a meaningful way. So now let's talk about how we draw things and how everything is handled in Pyleecan. The idea is that we have defined a generical geometric modeler. So that was the whole purpose of our ISM publication of this year, to explain how it works and why it's interesting. So the idea is that we have something that will create a generic representation of your machine. So basically it will be a collection of surface. And then once you have this collection of surface, you can do everything you want in a generical way. So if I want to draw a machine, I will have to draw every single part of it. So the first thing I will want to do, for instance, is draw my stator. So to draw my stator, I will have to start by drawing my slot. So if I start by the slot that I've defined in my lamination, I will call the build geometry method of the slot. This method is one of the most important ones for the geometrical modeler of Pyleecan. It will return to me a list of lines centered on the x-axis that represent the edges of my slot. So here, what I have. Then, when I come to the build geometry method of the lamination, I know that I have a slot that will return me a list of lines between 2 points of the bore radius. So what I need to do, if I want to draw the bore radius of the slot, of the lamination, sorry, I call the build geometry method of the slot. So I have the line that define my slot. And the lamination method to draw the bore lamination is very simple. It's just take the line of the slot, add a line for the bore radius, copy, rotate the line of the slot, add a bore radius, and so on. So that's very simple. You don't have to do some complex thing. You don't have to adapt it to any slot surface. As long as your slots follow what is intended to return by build geometry, it will always be available to be plotted in a lamination. And so what is interesting is that then if we want to define some more complex lamination, for instance, the slots are not evenly distributed, that's very simple. You just have to change the build geometry method of lamination, and it will just copy rotate in another way the slot. So that's very convenient to handle. And the last stage is the build geometry of the machine. It will call the build geometry of both lamination and assemble everything. So the idea is that at every single stage, you think of only something simple. In the slot, you just need to return the edge. In the lamination, you just have to draw the bore radius. So it's copy, rotate, and add an arc. Very simple. And in the machine, it's even simpler. It's just get the surface of all the lamination and return them. So you can see that all the complexity of drawing machines are shared and evenly distributed in the different methods. And what is really interesting is that the lines and surfaces of the slot and lamination object are something very generic and for Pyleecan. So we have surfaces which are defined by a list of lines needed to draw it, a label, so we can know what is this surface. For instance, it's a lamination, it's a magnet, and so on, and a reference point. The reference point is so you can apply some properties within the, you can add some property in FEMM, for instance. And what is really interesting is that all the geometry complexity is handled by build geometry. That means that in the code that we have to do the coupling with FEMM, we have only something like that. We call the build geometry of machine, so we get a list of surfaces to draw. And then for each surfaces, we take the list of line and we draw the line. So we draw the surface. And then we assign the surface according to the reference point and its label. All the geometry complexity is handled directly by build geometry. So the coupling is really simple. And what is very important is that as long as your coupling called build geometry, everyone that add a new slot, a new lamination, notches, uneven bore, and so on, as long as it's called build geometry, you will benefit from it in your coupling. And again, if you want to create a new coupling in Pyleecan, you can just call build geometry and all the complexity will be done. For instance, we managed to do a very short script. It's not much, it wasn't powerful at the time. Now we do something way better. That was enable us to create a 3D mesh in GMSH, and it was around 200 lines just because he was able to call build geometry. And we were able to define some very powerful lamination, as you can see here. So on the left, you have a lamination that was drawn in FEMM thanks to build geometry. And on the right, you have a very complex lamination that we showed to you last week. You can see that it's a lamination with 3 kinds of slots, but we were all, able to define it properly thanks to a specific lamination object. And then thanks to the build geometry, we add the proper surface and we were able to generate it with ease. Okay. So maybe we can have a first stop to answer some question about. So for now, I explained to you what is a GitHub account, what you can find to it, how you can open issue, how you can get the code on your computer, and what is the general ID of the slot. So the idea is that the only thing that matters is the build geometry methods. So let's see. Live example for drawing. In fact, I will just do a live example of defining the slot in a few minutes. In fact, so for the drawing, in fact, you can go back to if I find it to the issue. So. I've lost it. Okay. So, yeah, so again, I will start to do now the definition of the slot. And as you can see, the idea is that we want to create, we will have to create two methods to start. That's the very basics of the slot. So the two methods are build geometry. So I will need to draw the edges of the slot. So I will start by computing the coordinates of all these points and then connect them. So you will see that's not that complicated. And then I will add a second method so I can get this red area, which is the active surface of the winding. So I will get more in detail in a few minutes with that. Okay, maybe another question. Okay. So it seems that Emil and Helen are answering quite efficiently, so I will carry on with the presentation. So next thing now, you know that we will have to define build geometry and the get surface method. What we'll be doing next. So the second and most important place to go when you are wanting to contribute to Pyleecan is the pyleecan.org website. We have a development page that we need to reorganize maybe a bit, but you already have some very interesting contribution guidelines. So you can see, for instance, yeah, again, talk to it, open an issue and so on. And then we have some document about how the objects are organized and some coding convention that you should follow as much as possible so that the code has the correct quality for the global project. For instance, we have some naming convention and so on. And in particular, at the very bottom, we have the slot convention that explain to you what exactly is a slot in Pyleecan. Because for now, I'll show you the object organization, but then there is the philosophical organization. What is a slot, how we handle, what each method returns. And so everything is explained here at pyleecan.org/slot.convention. So the idea is that the method that I will define in few instance will be the build geometry method. And the idea is that we need to return a list of line objects. And these lines need to be closed, no, not closed. The endpoint, the endpoint of a line is the beginning point of the next line. So you can draw closed edges, I will say. And the first and very last point need to be on the bore radius of the lamination. And that basically is the two main constraints for the build geometry method, along with it should be centered on the x-axis. We ask to center it on the x-axis so that then we can take the slot and rotate it So you can generate the whole lamination. And so there are some other conventions, so you can see how everything is defined. What is very important, for instance, is that we define the height of the slot in a polar way. What the idea is that the height of the slot is the distance between, is the minimum distance between two circles that contain the full slot. For instance, here, if I put a circle here, I will have this point, and then the other limit circle is here. So the height of the slot will be here, and not if I put a line here, it won't stop here, it stops at the line of the circle. It's a bit counterintuitive, this kind of definition, because you will have expected that we will stop, for instance, here for the definition of the slot. Then it will be just H0 for plus S1 plus H2 for this one, for instance. But the idea why we have done that is because it enables us to define some generical method to compute the height of a slot. Because as long as you have the line that defines your slots, you can discretize them, and then you can just take the minimum and maximum radius of every single point. So you can get the radius of both circles, and then you can have the height of the slot with in a generical and numerical way. So that's why we go for this kind of definition. So if you want to go further, everything is explained here. And if you find something that that interpolate you, you can then talk about it on the issue. We are very open for discussion on the architecture of the project. So now, if I come back to my desktop, now everything should be downloaded. So here it is. So you can see that I have all the folder that was on the Pyleecan website. Everything was downloaded on my computer. So again, there is the EOMIS Pyleecan official repository. I did a fork, so I have my own repository on GitHub. So basically, is that I share with everyone what is the current state for the project, for my copy of the project. And then I take this part of the project and I put it on my computer so I can interact with it. So now I will talk a bit more about what is Git. This is a very important tool that you should be using for every single coding project, even if it's not related to Pyleecan. That's something very important because Git will enable you to track every single modification that you do on any single file of your project. For instance, if I go in Pyleecan, if I go to any file, I can do a right click on it. Thanks to Turquoise Git, I can then click on show log, and I have the full history of what was going on in this file. So I can see that I've changed it a few days ago. Just before that, it was Emil, and so on. So I can see what was going on. And if I go in the list, I can then compare with the base, so I can see what was changed. So I can see that on this particular day, I, for instance, renamed these properties, and I have changed, and I've added this new line, for instance, and so on. So that's very powerful. You always know what was the change, who made what, and why. Because if you take a look to the interface here, I can see that in this modification, Emil was about renaming issue as in issue fig, which is a new standard that we have added to the plot. But again, I can see what Emil has done. So I can appreciate the quality of his code. And the idea is that it's very important because when you will contribute to Pyleecan, you will send a set of modification of the file of Pyleecan. So when I will be when we will receive it, we just look into this kind of graph. So we will exactly see every single character that we have changed to every single file of Pyleecan. So we can know if you have done something that is interesting, or if we need to help you to understand why you can and how you can do better. So that's its benefit for the whole project. Again, it's helped us to gain a lot of time. Without that, maybe we'll have someone that will send us a zip archive with all the Pyleecan file and say, hey, I've changed something, now it's better. Is it right? Is it wrong? We won't be able to know. So now we know exactly what everyone changed and why. This is very powerful. And what is very even better is that you can ask Git, okay, this modification was wrong. Come back 2 weeks ago and give me the version of the file 2 weeks ago. When you are working on some scientific equation and then you realize that your result 2 weeks ago was better, you will be very glad to have put everything on Git, so you can just ask to Git, give me back my file 2 weeks ago. Because otherwise we maybe have 2 weeks worth of work to find where we were 2 weeks ago. So that's very convenient. And I really encourage you to use Git on every single project that you can, that it's meaningful for. And in particular, if you are contributing at several people on a project, you should use that. It will really help you a lot. So the whole idea of my contribution is that I want to send a set of modification to Pyleecan, so then someone can see, okay, is it some correct modification or not? So what I will do is that I will create what is called a branch. So basically it's a copy, it's an alternative version of the project where I will do some modification, and all the modification will be contained within the branch. And the idea is that then I will send this branch to my repository on GitHub, and then from my repository on GitHub, I will ask the official Pyleecan repository, okay, are the modifications with this branch worthy of being merged and included within the official Pyleecan repository and project. So I create a branch. I just basically have to provide a name. Okay. Yeah, and then I have to say to Git, okay, now use my branch. If I'm right, yes. Okay. So now I see that if I look at here, I see that every time I did a commit, I do it to the SciDC webinar branch. I will come back later of what is a commit. Okay. So now everything is ready. I can start to do the actual code of my slot. Because now every modification I will do will be included and shared with and added to the and tracked by my branch. So now the next step is how to create a class within Pyleecan. So let's come back to the presentation. So in Pyleecan, we have a very handy tool which is known as the class generator. The idea is that you don't have to write a single line of code to create a class in Pyleecan. In Pyleecan, all the complexity of object programming is just thinking about what should be your property and developing your methods. Everything else, you don't have to think about it. So it will be even simpler for you if you don't know what object-oriented programming is. We'll just say to you, okay, provide us with a particular file with these particular methods, and well, we will be able to handle it, and it will be included in Pyleecan. You won't have to do some very complex modification. So here it is. So the idea is that we generate every single class file of Pyleecan. The question is why? The reason is simple, is that we have around 200 classes files currently in Pyleecan, and the idea is that we want to have even more. Again, every single slot is an object, every single lamination, models, even input, output, and so on. Everything is object. So that's why we are getting close to 200 classes. And no one wants to maintain 200 classes file. This is something which is quite boring and that will create lots of errors. So that's why we have created the class generator, and you will see that it simplifies everything when I will show you what the code actually looks like. So how we managed to do that? Basically, we define every single object as a CSV file. So in the CSV file, I will show you just in a few minutes, we define the list of the properties of the class, we define the list of the method of the class, and few data and few metadata, and then the class generator will read all the 200 CSV file and generate the 200 Python code corresponding. So the first thing you need to know is when you need to create a class in Pyleecan, you just need to create a CSV file, which you will see is way more convenient. The second constraint that it put us is that then we can't generate the method because the method is actually the code of the class. For instance, for my slot, the method that will be geometry that will return the edges of my slot. So we have a constraint in Pyleecan. All the methods should be put in a very particular folder that I will show you in a few minutes. And every single method is in a single file. So it's a constraint, yes, but at the end, it's a very interesting one because the code is really easy to understand. We won't have a class with 2,000 lines in Pyleecan. It's, yeah, basically you can do it, but you shouldn't be doing it because every single method will be in different files. So it's easy to read, it's easy to maintain, it's easy to follow on Git because all the modifications on a file are only linked to one and a single method. So that's very convenient to understand. And finally, all the classes need to follow the same template. If we need to have a class that have a different method of initialization and so on, that will be quite tricky because of the class generator. We have found some workaround because there are lots of modification with the class generator. It's a very flexible tool, but basically everything is organized around the same template. But this template is already very powerful, so you shouldn't have to define something else. So the other benefit of that is that you need to define the CSV file to create a class. And it's this CSV file, everything is endorsed, so you have to define the documentation of your class. You will see in a few instances that you can't define a property without providing it the proper definition of what this property is, which is very important when you are trying to create a project where you will share your slot with everyone, or your models, for instance. If you have a property that is known as nmods, okay, nmods what? Nmod compute, nmod max, and so on. So you can provide some proper explanation about what is each property. And that's very important because anyone can then come to see the CSV file and you will be able to understand what it is. Then the idea is that as all the classes follow the same template, if we work on the template, we are able to easily add a feature to all the classes as once. For instance, very recently, we have added the copy method. So it was just a simple modification of the class generator, and automatically it was available in the 200 classes. Without the class generator, we would have to manually open every single file, modify, copy-paste the copy method, and so on. That would be a complete waste of time. But here with the class generator, we're just modifying 10, 20 lines maybe, we were able to add this very convenient method to all the classes of Pyleecan, which is very powerful. And last but not least, you will see that in the CSV file, you will have the type and minimum and maximum for all the properties. The idea is that we want to have some very constrained classes in Pyleecan. Normally in Python, you are able to do everything you want with your object. You can add some new properties. A property was an int, but you can provide it with a string or an object. You can do everything you want, but not in Pyleecan. We'll detail it a bit later maybe, is that we have a set of constraints. If the CSV file said that type machine is an int between 0 and 5, you won't be able to provide any other values. So it's a constraint because you have to follow what's in the CSV file. But at the end, again, we'll gain a lot of time because we can always be sure that what is in the object is exactly what we intend. We won't have a string in the type machine. It will always be an int with the proper values. And if the user tries to provide a wrong value or a wrong type, he will automatically get an error. So he will already have the feedback of what is wrong with his object. So that's very powerful and interesting. And again, if you type, we have also a property that enables to, if the users use machine type instead of type machine, the class generator will just say, okay, there is no property machine type. So again, we can avoid lots of error thanks to that. So I will just go now to what the CSV file look like. So if you go to the code of Pyleecan, so there are few files that are some global information of the project. So here you have the requirements. So every package that you need to install to have Pyleecan working. Setup is a file that enables us to do the release, for instance, the license, and so on. Here you have the tutorials with few notebooks that we definitely need to update. Maybe I'm practically sure that all of them are wrong now, but we will update them soon, I think. Here is the test. I will come back to them a bit later. So basically, it's all the code that we are using to make sure that Pyleecan is behaving exactly as we intend. And finally, here you have the main package, the main folder of Pyleecan. So a few general files for configuration. Here you have the method folder. So it's, as I said, as all the classes are generated, you need to put the method at a very particular place. So all the methods of all the objects are gathered within this folder. So if you go to it, then there is some global family. So if I want to add the method for the slot, so I go to the slot one. So here I have the folder for all the slot objects that we have, slot and holes. And here finally, I have the method of this particular slot. So this path is very constricted by the class generator. Here, everything related to the GUI. Here is everything related to the class generator. I will come back to it just a bit later. Functions are some global functions that can be used everywhere in the code. So things like how to save, load, and so on, logger, some material, some plot, and so on. Data, some machine plot, and so on, and some global data that you can use. And finally, the classes folder. So here you have all the classes of Pyleecan. And as you can see, we have one, again, we are around 200. So if I go to the class generator folder, you have the code of the class generator itself with few scripts that you can use to call it. And then finally, you have the class ref folder, which contains every single CSV file of the project. So if I go to the slot one, because we are going to create a slot, and if I open, for instance, this one, you will see the definition of the slot W11 slot. So we have basically two tables, the left one here, and the right one here. So the first one is all about properties. So every single line in this table defines a new property in my class. So for instance, for this schematics, I have W0, which is in meter, which is a slot isthmus width. I said that it's It's not a matrix, it's not something like that. It's a float. And I define a default value, and it's positive. So you can see all the data that I need to provide to the class generator so that he is able to define properly the property in my class. So again, when I will have my object, everything will be there, and we will check every time someone will provide a value for W0, we'll check if it's a float and if it's superior to 0. So I had a line for every single property. Then here are some global information for the class, the package. So it's a slot class. It's inherit from slot wind because it's a slot with winding. And here you have the list of the method of the class. So every single line here corresponds to a file in the method /slot/slot w11 folder. And here we have some global constant that can be again accessed inside the code. So the idea again is that the class generator will go to this file, scan it, and generate the code. So if I go to, in fact, I will start to run that. So if I go to the classes folder, I can find the slot 11 definition. And if I open it, you have all the code of it. And every line of this file, which is around 500 lines long. So again, it's not something you want to write yourself. Everything is generated automatically. So at the beginning, we have some general import of the methods that are then assigned within the object. The syntax looks a bit complicated, but the idea is that it's a very interesting feature is that as long as you don't call the method, if there is a package that the method uses that you haven't installed, you won't have an error, which is very important. If you want to use Pyleecan, but you will never use FEMM or GMSH, thanks to the class generator and this line here, you won't have to install it and you will have no error. So which is quite convenient. And here is the definition of the class. Again, I won't go too deep into the definition of it, but the idea is that for every single class, you are able to define it as a dictionary. You have the property with some default values. You have the possibility to convert your object to string, so you can display it. You can check if a slot is equal to another slot automatically. You can convert it to a dictionary, as I said. You can set all the data to none. And you have the getter and setter that enables to check every values of every object. But I won't go too much further on it, but the idea is that it provides you with very convenient options. So the class files are very interesting. And again, all you have to focus on is CSV file and method files. You don't have to think about everything else. Okay, so maybe a quick question on the class generator principle. No? Okay. So now let's start creating our slot, shall we? So I want to create a new slot. So obviously it's in the slot package. So I need to create a new CSV file. So normally I would just take this one, for instance, copy and adapt it. But I've done it before the webinar, so I will just paste it from somewhere else. But you can see that inside it, I have all the parameters that was defined on the schematics. So you can see W1, H1, D1, W2, H2, and so on. They are all there with proper unit, proper type, proper description, and so on. And then what is interesting is that you can see that I define only 3 methods for this slot. If you compare to the other one, there are much more methods. because I want to illustrate to you how easy it's to define some new slot in Pyleecan. Okay, so now I've opened my IDE. So I'm using Visual Studio Code. So it's a preference of mine, but you can use anything you want. In particular, within Anaconda, you have Spider. So let's just open the Pyleecan webinar one. So here I found everything. I can get all my code. So first, now that I have defined my CSV file, I can start by running the class generator. So I will have the run generate class, and I will just run this file with the proper Python. Okay. So you can see that the class generator is rather fast. Every single line corresponds to the creation of a single file. And once all the classes are done, we call what is known as black, which is a very convenient Python package that will basically reformat your code so that it looks nice. So it's a package that you should use as much as possible. So now if I go back to classes, I will see that that I have a new class, which is slot_DC, that was created by the class generator. Again, for now, the only thing that I've changed is the fact that I've added a CSV file and that I run the class generator. And again, I have already everything defined with the property and the proper methods, which is quite powerful. So now let's come back to the method folder. So a folder for each slot. So I need to create a new one. So with the proper name of the slot, so slot double cage. And then again, I will just get the code that I've prepared, and I will explain to you how it works. So unit, count, point, coordinates, build geometry, and get surfwind. So first, this is a non-mandatory method, but it's something quite convenient that we have started to do. Basically, it's just a method that will compute the coordinates of all the points. So you can see that, okay, I start by computing the angular opening of my slot. So I can have the coordinate of the first one. Then with some geometrical computation and some complex one, I am able to compute every single value. If I go back to here, for instance, I see that if I take the real part of Z1 and I add H1, I have this first center, then I can have the second one and so on. So you will be able to see my code in a few instances, so you can dive in to see all the computation are done. But basically, I'm just computing it. Something very interesting is here. I'm calling a method that is available in every single slot is outwards. Basically, the slot is asking the lamination that contains it, am I in an internal slot or an external one? Which is important if you want to know if you need to add or subtract H1. We'll show you a bit later what it looks like. And again, it's something that you should put in every single slot that you define, because you maybe want to use your slot as an internal one, but maybe someone will want to use it as an external one to put some magnet inside it. You don't know what the community will do. So the more general your slot will be, the more powerful and interesting it will be for the community. So I compute all the coordinates of my points, and then I return them. So again, it's not a very complicated method. There is just the geometrical constraints. Then I have the build geometry method. As all the points are computed in a separate folder, in a separated file, it's very simple. I just take all the coordinates of all the points, and then I create the list of line. So first line is a segment between Z1 and Z2, then it's an arc, then a segment, another arc, a segment, and so on. So you can see that I define line by line the edges of my slot. Again, the properties and again, segment and arc1 are objects of Pyleecan, so you can find their corresponding CSV file within the class ref folder. And last but not least, get surface wind, which is a method that will return this red area. So basically, I just call bGeometry. I remove both these lines and add a segment to close it. So this line here. So now I have a full closed surface, and then I just have to create the corresponding object, and I return it. It's that simple. And now with that, the slot is already available in Pyleecan. I can draw it in FEM if I want just now. But I will show you more in this notebook. So here I will be using the Pyleecan version that is on my computer. So I provide the path to the folder in here. It's not a notebook that we have shared because we'll see that it's a rather short one, and it's not the notebook itself is not interesting. It's more what I will show you that which will be. So as I've run the class generator, the slot DC class exists, so I can import it. Now I can define the slot lam slot object. So it's a lamination with empty slot, and define it with a slot DC. So I've started with an internal lamination, external one, sorry. So I can already plot my slot. Again, for that, I'll just call the bGeometry. I have the edges, and then duplicate, rotate, and bam, I'm already available to plot it within the lamination. But there is even better. So here is another example, but with an internal lamination this time. But what I will do is that I will provide a user-defined winding. So it's a theoretical one that we use only for testing, so it doesn't make sense at all. But it's to show you that we are able to automatically cut the surface of the winding. So I have just defined the global surface, but you can see here that I'm already capable of cutting it and define a different phase in every single part of the winding. So of course, for this slot, it doesn't make sense, but that's very powerful because I already am able to handle double layer or even 4 layers winding here. And I can even do some other and more complicated number of layers if I want. And because everything is built around generical object. The get winding surface return me a surface object. And I know how to cut a surface. Okay, I provide a line, I check if there is some intersection, and then I add some lines to complete it. So we have a method to do that automatically. So you don't have to do that. And again, that's quite very powerful. And again, you have already all the method from the slot abstract object. So here, for instance, if I type slot.comp_height, I have the height on my slot, and I have not developed this method yet. But I can already do that. Basically, I just call bGeometry. I discretize every single line defined by the bGeometry methods, and then I try to get the minimum and maximum absolute values of each of complex points. That's what I showed you a bit before about the slot convention. But again, without having to define it, it's already available, and I can go to FM directly. And you can even check here that if I ask for the help test of my comp height that it's really the slot method, and that the build geometry is the slot DC1. So here it is with only two, so three because it's a bit better, but the third one is not mandatory. But we just build geometry and get surface one, we're able to draw any slot. I just need to have the edges and the surface within it, and then it's already available in Pyleecan. So that's quite powerful. Maybe is there any question at this point? Or can I go further with all the other methods maybe? Yes, actually, yeah, but I said that this winding is a fully theoretical one for testing and plotting, but it doesn't make sense at all. I fully agree with you. But that's interesting to show you that with very few lines, I'm already able to do that. But if I want, I can define a very simple one that won't cut at all the winding, which is more convenient and suitable for this kind of slot, obviously. If I'm able to do something complex and crazy, I can do something simple. Yes, yeah, that's the very point. Thank you, Emil. Again, you can do some very crazy things with the build geometry methods of Pyleecan. You can create some machines that don't make sense, but maybe when you will try to actually simulate it, you will see that it makes more sense than you thought. So that's why it should be possible. Okay, then, so now I will add the other methods. So method to check if my slot is okay, to compute the opening, the height, and so on. The idea is that I show you that all this method is already available in my slot, but it's always numerical. So you don't want to discretize your whole surface and then do some very long and complex computation when you can say that, okay, the height of my slot is just h2, for instance. You don't want to lose some time with that. So here are some other files. So you have, if I take a look on it, you will see that here is the height of my slot, and I had this particular arc that I told you about a bit before, sorry. And here is a method to compute the surface. So it's simple. First, it's a half circle, then it's a trapeze, half circle, and so on. So I compute every single surface, and then I return it. It will be way more faster than just computing it. And so now I just need to add the proper method within the CSV file, because the class is what is inside the CSV file. Now I have added the method file within the method folder, but the class generator doesn't care about it. He only cares about what is inside the CSV file. So if I run again my notebook, even if the methods are there, they won't be used because they are not defined within the class. So I add all the method. No, it doesn't want. What? Okay. So then I can come back to my class generator script. I'll run it again. And if I come back to my notebook, I will restart my notebook so that I will be able to import again the classes, because now it's different. So I need to restart everything. But as you can see, it's quite quick. So black is reformatting. I will just wait a bit for it to end to avoid any surprises. And I will prepare what is next. And done. Okay. Again, all the 200 classes were completely written. So now I import it back again. So I'm still able to draw it, which is nice. And now if I go take a look at the comp height method, you will see that it's really the one that I just added. So I should have the same results, which is quite nice, but it's faster now. Okay, so here it is. Now my slot is fully complete. I've done something in the script to know if everything is right, and the slot looks right to me. But the problem now is that I don't want my slot to look right to me only. I want my slot to look right for all the Pyleecan community. So the next step is I need to provide some tests to show and prove to everyone that my slot is working as intended and that it will always work that way. So for that, again, I've prepared a small script for that. So I will put it in the proper folder. So obviously the test one. So in the test folder, we have the test for the classes, the functions, the UI, the methods, some tests that are gathered for all the plots. So we can see that the machines are correct and that the post-processing looks right. And the validation cases, which is the most important one, that will run some full simulation and check that everything is okay. And so here it's a method that I want to check. So I go to method slot and I add my own file. Okay, let's dive in a bit in this file quickly. So if I take a look at what is inside. So the idea of test file is I will call the method of my slot and say, okay, when I with this slot, if I call comp height, I expect this result. And I provide it as in a standardized way so that anyone can call it automatically. So every time someone contributes to Pyleecan, we can just run all the tests and check that everything still returns what it returns previously. So here is you have a very interesting syntax. Is that we define two lamination. So it's the two lamination that I just show you in the Jupyter notebook, in fact. And here I provide a dictionary saying, okay, if I get this lamination, I should have this surface for the winding, and this height. And here is the definition of my test. So what I do here is that I had I provide the dictionary as an argument, and then it will call this test for every single definition within my dictionary. In fact, it's more list, but. And what I do is just I call the comp surface method of the slot, check if the result is correct, but I do even better just afterwards, is that I call the slot comp height method, which is very interesting because I call the analytical method with my values, and then I call the numerical one by discretizing my lines, and then I check that both methods return the same results. So I'm really convinced that my slot is perfectly working when both methods return the same thing. And at the very bottom, I have another test that that will check, okay, the distance between the first and the last point, is it really W1, for instance? So I can check that my schematics is really what I intended. So again, I just provided that in a general and standardized way, so that when it will be shared on the Pyleecan folder, everyone can be able to run it. so that in 3 years later, if someone modified my slot and broke it, for instance, because he wanted to introduce a new parameters but failed, when he will run the test, normally he should see it. So he will be able to see that something is wrong and that he needs to rethink his modification. So if I want to run the test, I will just use this syntax. Everything is explained more in detail on the Pyleecan website. We have a full, tutorials on that will be shared in few days, I think. That will explain you in depth how you can define it. But just the only thing you have to know is you can take a look to the files that correspond to the object that you are trying to implement, and then you will be able to take some inspiration. So in fact, if I go to okay, so I ask it to run this file and this file only. And it run every single dot here is a test that passed. So you see that I've run 12. If you take a closer look at my file, you will see that I've defined only 6 tests. So it's 6 tests multiplied by 2 laminations that I've provided. So that way I'm sure that my slot works both for inner and outwards lamination, which is very convenient, so I can confidently share with the community. I know that the community will be able to use it properly. So now the slot is complete, finally. So I can just, now everything is done on my computer, but now I want to share it with the project. So the first step is to say to Git, okay, I've done some modification. Please track these modifications, they are meaningful. So I will click on commit, and it will automatically scan my whole folder and check what are the difference between what's on the computer and what are on the server. So you can see every modification that I've done. In fact, which is quite interesting. Black, what was run by the class generator, I've changed and reformatted some files. So you can see that here, for instance, there are a few modifications that was detected by the commit GUI, but it's not a meaningful one. So I say, okay, I don't want to share that. Then it's important to know that Git won't track any file if you don't ask him to. So I will select all the files that I've created, so the test, the class, the CSV, and all my methods. So it's all the file here, and then I add them to the commit. So I say, okay, here is the set of modifications that are important to share. And then very important here, I put a message to say to all the community what I've changed. So for instance, here, I will just type NF. So it's a coding convention that we have. It's mean new feature. We have over on the website if you are interested. Adding slot double cage. And then I push commit. So now these new files are officially on my listed on my computer as a set of modifications which are meaningful. Then let's say that, oops, I realized that I did something wrong in the code here of the surface of the slot DC, for instance. So I have done a modification. What is interesting is that you see that VS Code is directly linked to Git because he is able to show me that this line is modified according to the reference. That's one of the reasons why you should be using a proper IDE. And then I can just go back to Git, commit. And again, you can see that I have the modification that is here. and I can click on compare with base, and I find back my modification. So I can add a second commit, for instance, code cleaning, fixing docstring. So now I have a set of 2 modifications, but they are on my computer. Again, all this process is not fully linked to Pyleecan. It's a link to Git, which is a tool that you should be using for any of your projects. And the procedure that I'm about to show you is how you can interact with any open source project. So now I have, so we have the EOMIS global repository, which is the official one. I have my copy of the repository, which is the fork. Then I have cloned the data from my repository on my computer. I have done some modification on it. I have created a branch with a set of this modification. So my branch is currently having 2 commits, so 2 sets of modification. And now what I want to do is I want to share it with the community. So the next operation is to send my modification from my computer to my repository. So we'll detect my branch, and I will send it to my repository. So I do what is called a push. So I take my data and I push it up to the repository. Up, and now it's online. So now if I come back to GitHub, so here is eomis/Pyleecan. But if I come back to my fork, GitHub is a very nice interface. You see, okay, you just share a new branch with some modification. Is this branch ready for a pull request? A pull request is saying, okay, here is a branch with a set of modifications that are ready to be included in Pyleecan. Do you want to put it into the project? Again, it could also be a push request, but in this case, it's named a pull request because we take the side of the project. So it's just simple. I just click on this button, and then I say slot DC webinar. Here is a pull request to add a new slot CF issue. And something very interesting about GitHub as well is that you can have you can find some link automatically. I will show you that. So you can see that the issue that created where we talk about the slot is named is this number. So I can just take it. And if I mention it in my pull request, it will in fact automatically create a link that I can follow to the issue. So that's very convenient. That way you know what is going on in the project. So basically now I can just say create pull request. So if we come back to EOMIS Pyleecan, I presented you the code tab, the issue tab, and now there is the pull request tab. So you have all the pull requests that are listed here, so that all the modifications that are waiting to be included in Pyleecan. So I can see here is my commit, so I can see both of them. So I can see that the commit here is just about adding the different files and so on. So I can see everything. And here I have the list of changes done by the pull request. So in this one, it's very simple because I'm only adding some new files. But if you go to a more complex and normal one, I will say, there is more files modified in this one. You will see that I have all the history of modification. So that's very convenient. Again, I know exactly what the people have changed in the project, so I can check, okay, should we allow this modification to be done in the project for everyone? So that's very, very powerful. So now the pull request is available on the EOMIS repository. And now either me or either Sebastian, the other maintainer that I have the right to merge it, will say, okay, I've checked it, everything's look right, we can merge it and include it to the project. And once it's merged in the project, everyone that clone it will get the corresponding code, and it will be included in the next release and so on. So that's the whole process to add a slot in Pyleecan. That's a lot of information. There are lots of things that we haven't talked about, but it's more general about Git. It's a very powerful tool that you need to investigate more further to understand really what you can do with it. But at least you saw every single step that you need to do to add a slot. Again, the only thing missing is me clicking on validated to merge the pull request. But you see. Is there any question now? Yes. Let's see. Okay, so the question is, so I made an axial symmetry copy of the slot. So first, you can do basically everything you want in Pyleecan as long as you provide the proper object with the proper bit geometry method. For instance, here I have a slot which is fully symmetrical, but I can have decided to do something else. And as long as I provide the full list of lines that draws the edges of my slot, it will be available in Pyleecan, even if it's not symmetrical. That's the first part of the answer. The second one is that if you look at the code, in fact, you will see that we have already done some interesting classes. Basically, every time you want to see if there is if something exists in Pyleecan, you can take a look at the class ref folder. So if I go to machine, I can see that I have lam slot multi class. Obviously, I know it, but it's something that you can talk about it on issue. You open it and we'll go and take you back to it. And you can see that here I have a slot list. So I provide a list of slots, and then I have alpha, the position of my slot. Again, I say that in the bit geometry, I draw the edges of my slot, I add the border radius, I copy it, and so on. Basically, if I go to the bit geometry of lam slot multi, you will see that instead of copying the line of the slot, I will just call the bit geometry of every single slot in my slot list. And then for the border radius, I don't assume that they are constant. I just check what is the position of each slot and what is the angular width of the slot. And then I know that, okay, the end point of the slot is here, the beginning point of the next slot is here, so I need to do this line. And you can see that it's very simple to create some very complex machine in Pyleecan. You just have to define the new bit geometry. And in particular, if I want to define a lamination that, for instance, has a yoke that is not circular, I will just provide a new object within my lamination object. And in the bit geometry, instead of creating the surface, I will just create the surface corresponding to this yoke object, for instance. So that's very powerful. In fact, I told you about the fact that all I need is the edges of the slots and the surface of my winding. And in fact, I can prove you that it's really only that. So here is a new feature that we have added this week. So I can now open a DXF file. So this one is only the previous one. It's quite simple. I can zoom in with my mouse, And then I can click and select the line that will define my slot. Then I can click on plot, so you can see that I already have defined a new slot. It's that simple. And then I can say, okay, I want my winding to start as the for line and end at the third line and end at the fourth one. So I can create this one. So in a very few clicks with the DXF import, I'm able to define a new slot with a new winding for the previous. So now if I just click on save, you can see that now my machine has changed and now I've completely redefined my winding. Again, I only need the edges and the winding surface. Then you can do everything you want. And if, for instance, I can then go even further. I can take my lines, do copy, rotate, translate, and so on. I can completely change it. I can do a parameter sweep around the position of every line. I can do everything I want. It's that flexible, it's that powerful, thanks to the possibility that as long as I have the build geometry and the get surface wind method, I can do whatever I want. So behind what I just showed you, I have a slot user defined object that just contain a list of lines and the index to create my winding surface. I just need to store it because now, thanks to the DXF interface, I'm able to conveniently define this list of lines, and then it's that straightforward. And what is neat is that I can do the same for all. So here it's a bit more complicated. I just need to define all the several surfaces. Every time I close a surface, the software automatically detects it. Then I can check, okay, what is this surface and so on. And then I only say, okay, this is a magnet, this is a hole, this is a magnet. So then I can plot it. So I've changed the whole of the previous in a few seconds. Again, I have a whole user-defined object which just contains a list of surfaces. So now I can save it. Sorry. And boom, it's available as an object. And now if I take a look at my new Prius, I don't know if this one will be more efficient, but at least I am able to create it. Again, as long as you provide Pyleecan with the proper surface, the proper edges, and so on, the geometrical modeler is flexible enough to let you handle everything. For instance, if I want now, I can go into the script, take the list, these three surfaces, do a translation to put it on 0, do a rotation, another translation, and provide the new list of surfaces to Pyleecan, and boom, I will have returned the previous magnet. It's that simple. I just, again, as long as it's in the black box that return my list of surface, whatever is inside the box, it works. Just a small disclaimer, for the slots, everything works as intended for now, but we have a small issue on the magnet, is that for now we are not able to have the magnetic, the magnetization direction of the magnet. For instance, as now I know that I have a surface that can have any shape, which is a magnet, but I don't know in which size I should put my magnetization. So there is an open issue about it on the website. So if you are able to find us and help us to find a convenient way of finding what is, sorry, it's this one. So if you find a convenient way of taking any surface and say, okay, the global orientation of this surface is there, that will greatly help the project. But it's a discussion that I will carry on anyway. We had some new ideas since yesterday, so we should find a convenient way of defining that. So here it is. So you can see that you can define a new slot very easily by providing only 2 method files and a CSV file. And I also show you with that the DXF, you don't even need to define this slot 1. But again, here is a very interesting feature that I show you for the DXF import, but we can even extend it so that we can read a DXF file, for instance, to create the board radius and so on. So we can do a lot of things for the topology. You can go on the issue page and filter on topology to see what we are currently discussing about. But I'm quite confident that we can draw some very interesting and complex machine. So now I will take some few questions. Yeah, and something very also important is that by the DXF import, as I'm able to extract the slot, then it's the bit geometry that draws the machine. So if I want to draw the slot only once, I can. So I can extract a slot from a DXF file and benefit of all the symmetry properties of Pyleecan, which is quite very nice. Okay. So if there is no further question on the topology, how to contribute to the topology part, I will let Emil talk to you about how to contribute to the model part. So thank you for your attention.
Hello everyone. So we are going back to the Github website. So just to look at the different issues that we already have, and we worked a lot on this this week to prepare the webinar. So here it is, and to better organize the issues and regarding the global Pyleecan project. We have opened a general issue in which we describe the roadmap development of the Pyleecan code, and regarding especially the performance optimization of electrical machines. So here we have some, so the link to the Pyleecan project, which explains a bit more the general idea of the project. And then the aim is just to focus more on the on the Pyleecan developments. So when we speak about performance optimization of electrical machines, so first we have to compute electromechanical performance, so torque, power, torque ripple. Then we also have to compute motor losses, joule losses, iron losses, magnet losses, other losses such as converter or mechanical losses. Then for motor design, we are also very interested by calculating the temperature which is generated by the losses. It will influence a lot the design. And if we want to calculate efficiency, then we also need to speak about operating cycle, duty cycle, so how the electrical motor will function in a more realistic way. So for this, we can base the work on standards, and for HEV applications, for example, we have the European standards or the world standard, WLTP, or other standards. And then a last aspect is also to optimize on the control strategy. So once we have the possibility to calculate the efficiency depending on the operating cycle, we can work on the control strategy. And for this, for example, we talk a lot about MTPA or MTPV for EV HEV applications. So that's basically the roadmap that we can have if we want Pyleecan to be able to optimize the performance of electric motors. So then, so having this in mind, the question is how we organize all the subtasks, all the small issues that we'll need to create to go in this objective. And so for this, so we propose to focus on basically on Pyleecan objects, so machine objects, input, output objects, models as well, and to talk about PMSM, switch reluctance machine, squirrel cage induction machines, etc. To talk about input-output, so it will be the performances, the losses, the temperature, the control strategies, the standard duty cycle. And then finally to talk about models. So it can be electric equivalent circuits, it can be magnetic simulation using this software, FEMM using other software, Elmer using couplings, couplings with commercial or free software. And finally, we'll be able to organize all the issues based on these keywords and based on the labels that Pierre presented before. So we can have a very clear organization for the Pyleecan roadmap. So we also add new issues to illustrate this a bit more in practice. So we have an issue on the iron losses calculation. So I can show you how it presents. So basically it will be so here a new feature, and then some contributor which will describe the aim of the new feature in terms of milestones. So first we need to define the input outputs of the model. We need to see if it already exists somewhere as Python code. And then we need to decide exactly how we'll implement this in the Pyleecan project. So this issue about iron losses. We also have an ongoing issue about the coupling with Elmer and GMSH for the 3D electromagnetic calculation of squirrel cage induction machine. And we also have ongoing issue on the electrical equivalent circuits of squirrel cage induction machine as well. And then we have created, as I said, several issues, and for the moment, nobody is working on them. So I can sort all the issues following the help wanted label. So all the issues where we need contributors. And for example, here we'll have an issue to develop the coupling with ANSYS, because if you remember, and if you were here during the first webinar, we made a survey, and we wanted to know which software would be very interesting to couple with Pyleecan. And there were three software on the top. So the first was FEMM, and then we had ANSYS, MotorCAD, and Flux. And so all of this coupling, we can organize them directly using the Pyleecan GitHub. Okay. So yeah, we have MotorCAD, we have AlterFlux. That's already a good start. And so if you have some knowledge about this, if you already know how this software works, how to make workflows, how to make coupling, then you are feel free to participate, to open new issues. This will be very useful for the whole Pyleecan community. Okay, so we can go back to the general presentation. We have talked about the issues, and then maybe we can just focus a bit more on how to contribute to Pyleecan models from an architecture point of view. So as said Pierre before, and during the previous webinars, in Pyleecan, everything is basically an object. So we have objects for topologies, simulation, input, output, for models, for post-processing, for plots. Anything is a model. And then a Pyleecan simulation always starts from an input object and always returns an output object. and a simulation object will generally run several models, or you can just run one model, and for each model there will be an output object at the beginning and an output object at the end. So this is the illustration of what Pierre talked about when he said black boxes. Here we really have a sequence of models, outputs, simulation objects that can be seen as black boxes. And so there is still one question, is how we generate the first input object, because any models needs an output at first. So when we begin the simulation, the first input object will generate the output object. And if we talked about standard methods, then this input object will have a method which is whose name is gen input, that will create the output object. And from this output object, we can start the model simulation, the model execution. Then this model object will have several methods, and the first will be run to execute the model. But then we also need to calculate, for example, the time and the angle discretization. And for this, we use comp axis. This is Helen will talk about this using SciDataTool. And then we also need to generate the output. And so for this, we'll have the method store output. And since the output is a method object, is an object, then it has some specific standard methods such as plots or post-processing and post-processing. Yeah, that's basically the principle. So all the models should work like this. And then, so when we are talking about models, we are, for example, talking about the model that we use for the magnetic simulation. So here we can have, for electromagnetic simulation, several models. And the principle is to use inheritance, such as for lamination or for slots. And to start from a standard magnetic object with standard outputs. So here, for a magnetic object, we'll have the air gap density flux, we'll have the torque, we'll have the winding flux in the stator at stator side. And then we'll create a new model using the magnetics standard object. And here, for example, is the magnetic simulation using FEMM. And so we'll have the standard methods that are available and that we can override or not. And we'll also it will also be possible to add specific methods that are really related to the complexity of the FEM simulation. So here first we'll have to draw the geometry for all the machines, for any kind of machine, so using build geometry. And then we also need to solve the FEM problem. And so for this, we'll call the appropriate method solve FEMM. And what is very powerful is we can copy this way of doing for any kind of magnetic models because we agreed on the standard outputs and we agreed on the standard methods. So Elmer here will draw the geometry using GMSH and we'll solve, we'll have a method to solve the problem. So now we can discuss a bit more about the outputs and how we store the data in the outputs. And for this, I will let Helen present you what we have already in Pyleecan.
Okay. So now that you want to develop in a model or build a new model, you will need to know how to store your data and how to use also the input data or the axes. So first you need to use the computation axis. and also to store it. So you need to understand the structure of the SciDataTool objects. So last week I showed you some details about the general structure and the get-along methods to extract data and the plot methods too. But if you want to develop in a model, you will need more knowledge about SciDataTool in order to correctly create them with all the information that you can and to use their full potential. So as I showed you last week, there are 5 main objects in SciDataTool. So first we have the axes, which are 1D data. So either you want to store the whole vector and then you use the data 1D, or you know that your axis is a lin space. So you only store the first, the last value, and the discretization. Then you have fields which can be stored in the time-space domain or in the frequency domain. Those fields are defined on a list of axes. So they contain the information, all the information about axes. And finally, you may have vector fields like air gap flux density, for example, if you have a radial and a tangential components, for example. Now we want more details about those objects. So here is a UML chart of those objects. So here you can see the inheritance between the classes. You can see on the top the properties of each object, and at the bottom of each object there are the available methods that already exist. For example, you can see that data lin space and data 1D have the same methods, but have different properties. So initial, final, and number for lin space, for example, whereas data 1D has only values. All those objects share a name, a unit. Those are very important because when we want to use plots, then it's very useful to have all this information. Now I'm just going to go to a CSV file to show you what it looks like. So we can go on GitHub maybe. So if we look, for example, in the generator, if we look in the output, this is where all the data will be stored. For example, if we look at out elec, so that will also be the starting point for the magnetic module. We can see that we have SciDataTool objects. So here, for example, time is a SciDataTool object. So it can be a 1D, data 1D or data lin space, it doesn't matter. Then we have angle, and we also have output data like IS and IR, so the currents, for example. If we go into out mag for the magnetic modules, we also have so B, which is a vector field. We also have the torque, which is a data time or data frec, the flux linkage, etc. So all these objects need to be stored in the outputs. Okay. So how do you create them? So when you create a SciDataTool object, you need to specify all its properties. So for example, a simple example, if you want to create a time axis, you need to give it its name. So the name is very important here, because then if you want to do a Fourier transform, SciDataTool knows that the equivalent of time in the Fourier domain is frec. So if you don't name your axis time, you won't be able to perform a Fourier transform. So it's very important. It's good to provide units to label the graphs. So you provide the values. And I also talked last week about symmetries and normalizations, which are very useful to reduce the storage data. So if you know that your time axis is anti-periodic, for example, you will only store 1/8 of the data. And normalizations, it can be used then in plots if you want to change, for example, for your FFT, you want to use electrical order instead of frequency. It's very easy. And you don't need to store additional data. It's just a dictionary here. Here is another example with data lin space. So in Pyleecan, we mostly use data lin space because our axes are almost always lean spaces. And here is an interesting thing is here on the left, you can see that we have a period of 12. So we can either define it as the final value is 2 pi divided by 12, and the number is also divided by 12, or we can define the full angle up to 2 pi and with 2016 points. And then if you want to get the periodic part of this axis, we can use this, this SciDataTool methods, get axis periodic. You say what is the period, and it will extract and create the equivalent data objects with the periodicity. So it's very handy, and it's used a lot in Pyleecan. You can also have like special axes, as I call them. So like phase, for example, you know the occurrence have 3 phases: phase A, phase B, phase C. But you don't want to do mathematical operations on A, B, C. They are letters, they are not numbers. So to do that, there is a key here, is components, which says that this axis is only like components of a field, and we shouldn't do mathematical operations on them. So you really need to use this if you know that your axis is letters or integers that shouldn't be multiplied or anything. Okay, so now how is it handled in Pyleecan? So the computations axes are automatically computed from the discretizations that you want. So when you start a model, you say, okay, I want 2000 points in time, etc. Then Pyleecan will look at the machine topology and detect if there are periodicities. And it will look if it can use these periodicities. For example, if you have a known number of time steps and I don't know, a periodicity of 2, it won't be able to use the periodicity. So it will print a warning to tell you that. For example, for time, if you specify the rotation speed, it will automatically compute the final time. So it's very handy. So if you want to have a look at that, we can look at the comp axis method that is present in every module. So I'm going to look at it in Github. You can look at it in your folder as well. So this is in methods, simulation. Let's take the magnetics module. So here we have the 3 generic methods that Emil has just talked about. We are going to have a look at comp axes. So here the idea is to take the data object from the previous module. So that is to say here the electrical module. So we copy it. And then so these axes always are full. They don't include periodicities because we always want to be able to get back to the full axis. But then for the computation, maybe we have periodicities, and it would be much faster to use FEMM, for example, on 1/12 of the machine. So we are going to get the machine periodicity. You can have a look at this method later if you want. And then we will create the new axis using this function, which is basically a call to get axis periodic that I showed you earlier. And so we will do that for all the axes. We will also get the number of time steps which can be used in the model later. And we will store all these computation axes in this axis dict variable, which will then be called in the module. Okay, so now we'll let Emil continue about the module, and I will come back to talk about how to store then the output.
Yeah, thank you, Hélène. So this is the first step of the magnetics module. So it is a method of the magnetic standard standard simulation. And now I will just go so in run process, there is so first the calculation of axis, and now I will go into the method that will calculate the air gap flux directly. So this method is for example in the simulation object MacFem. So to calculate flux using FEM. And here, so this method is here. We have the axis dict, which is given as argument of the function. And at the beginning of the function, we just get the axis that we'll need for the simulation. So we'll have angle and time. Then we can extract the values using SciDataTool function. And so we have now the angular vector and the time vector. We also get the angular position of the rotor for each time step. And from this, we already have imported all the geometrical, all the axis information. And now we also need to import the results from the previous output. And so the previous output is the electrical output. And from it, we expect to get stator currents and maybe rotor currents. And so for this, we'll basically call the electrical output using the method comp_i_mag, which will return the current. And what is very interesting here, and this is provided by SciDataTool axis, is the fact that we give the time discretization of the magnetic module, and the electrical output will interpolate the currents given the magnetic time discretization. And this is very important because you can have models that have been calculated with different discretization, and then when you want to chain all the models, they need to agree on the time and space vector. But doing so, they agree automatically. So here we have the currents, and then we start the FEMM solving process. So for this, first we need to draw the geometry using draw FEMM. So here we have the magnetic model, which is in FEMM, and then we need to solve the magnetic model, the FEM problem. And here we have the distinction between FEMM parallelization or not. And this is only driven by one input parameter of the model, which is the number of workers. And then we store all the outputs in the output dictionary. So just here we have an example of how we store basically the radial flux matrix inside the output dictionary. All right, so here we can go out of the complex air gap function, and then we need to store the outputs. So to store the outputs, there is a generic method inside the magnetics object that will store all the standard outputs. So I can maybe let Helen explain a bit more about the SciDataTool object.
Thank you. Yes, so to store in the output, you need to know how to create fields and vector fields. So I'm just going to go back to my presentation. So to create a field, it's the same principle. You need to fill all the properties. So again, a name, a unit, the symbol will be used in plots for the y-axis, for example. Very important, the list of axes on which the field is defined. If the axes do not match the field, then it will raise an error and it won't be able to create the object. It's very important that the axis is has exactly the same shape as the field. And if the axis is periodic, then the field must be the size of the smallest period, of course. So here on the left, you have an example. If you want to store in the Fourier domain, you can use data frec instead of data time. And of course, your axes need to be a Fourier axis. So here, for example, frequencies. Here, for example, we have used the phase axis. So for example, it was ABC. So that means that our IS matrix must be size 3 and the number of frequencies. On the right, you have the slightly more complicated case is when you have a vector field. So each component is a data time or data frec. So here we have two, for example, a radial component and a tangential component. So you define them exactly the same way as before. And then you need to add them to your vector field object, so which is the class, the object that englobes all your components. And so it's the component, sorry, again. It's the component attribute, which is a dictionary, which will be filled with radial, tangential. It can also be used with X, comp X, or comp Y, comp Z, or actual. And then it has nice methods to extract the data. I will show you that in a minute. I just wanted to show you the store output method. So here we are. So it's exactly as I just showed you. So you create the axis list. So the time and angle here, for example. You initialize your vector field object, and then you store each component, so the radial, tangential, and axial ones, and you add them to your vector field objects. Here are other fields to be stored in the output. So for example, the torque. Here it's simpler, it's just a data time, and it has only one axis, it's time. And here are other outputs which are not SciDataTool objects, so they are easier to handle. You have the winding flux, which depends on phase and time here. Well, it's the same. So just one last thing, I just wanted to talk more about the extraction part. So as Emil just told, you have the computation axis, but your data is not necessarily defined on those computation axes because the axes may come from a previous module. For example, the currents were defined on the time and angle were on the time of the electrical module. They also may come from an import. If you want to import a flux from a third-party software, maybe the axis won't be the same as your computational axis. So you will always, the best way is to always interpolate the field on your computation axis. So here I'm just going to show you an example in the fourth module. So simulation, I will go to here, Maxwell tensor. We have a small method to compute the forces using Maxwell tensor. And so here, for example, we take the computation axis, angle and time. So here are the full axis. And then, these are with the periodicities that we want to use. And we get the values of those axes with this get values methods. And then we want to extract the air-gap flux density to compute the force. So to do that, there is a method from SciDataTool, which is get r phi z along, which will return all the components in the cylindrical coordinate system. And it's very handy because if you don't have, for example, an axial component, it will return an array of zeros so that you don't have to worry if you had all the components or not. So here, what I wanted to show you is here you say time equal axis data, and axis data is a dictionary of the time that is your computation axis. So that means that SciDataTool will interpolate the field along this data that you provided. So this should be the standard way of extracting data in all Pyleecan. Okay, I think this was it for me. I don't know if you have questions about SciDataTool objects or the physical models, how to implement one. No, there's no question. Okay, so I'm gonna let Pierre finish for today. Thank you.
Thank you, Hélène and Emile. So, it was a lot of things to talk for today, and we have even other things that we could have talked about. But as you can see, there is a very large range of what you can do with Pyleecan. So we try to talk with you as much as possible, but it will be always complicated. So if you need to remember only what message is, go to the issue page of Pyleecan. That's where we will be able to talk to you and explain to you how you can contribute to add your new model, or you can contribute to add your new slot, and so on. So always go to this page so you can contact and talk with the community. Pyleecan is all about sharing and discussing about what can be the best architecture, the best model, and so on, what are the correct values, and so that what are the correct flux that should be written by a model, for instance. So we need as much feedback as possible. In fact, lots of things that we show to you during the webinars are only there because people challenge us by asking us, okay, can you do that? Can I add these new models, for instance? It's because someone try to implement MAG Elmer that we take the opportunity to rethink about all the architecture of the models. That was very helpful for us to be challenged on that so that we can do something more efficient. The architecture of Pyleecan is always changing. We are always looking for new things to improve. In fact, what I show you during the DXF import is very new, because at the very beginning, we didn't think about how far this architecture can lead us. At the beginning, we use a slot user-defined to just use a snowflake machine that you may have seen in a previous presentation. But you can see that by taking the concept one step further, we can do something even better and even more interesting. So that's why we need always people to talk about Pyleecan, try it, try to simulate some complex machine, to add new models and so on. So yeah, so that's why even if you don't have time to actually contribute to the code yourself, please still go to issue of Pyleecan. You can, it's something I didn't show you. Is in Pyleecan, you are here the possibility to be notified every time something happened on the Pyleecan repository. So if someone asks a question, if someone provides a new model and so on, you will be notified. If you only have time to discuss with us, to share with us some new publication, to debate about how should we organize everything, that's still very precious for us. So please come and contribute with us on Pyleecan. So I think that's it for today. Maybe, I don't know if you have any last question, but okay, so I hope to see you, all of you, in the issue page of Pyleecan one day. So again, we are really glad if you find a way of challenging this architecture. Every time we find something that we are not able to implement, it's a new challenge, and it's a new way of, okay, how can we organize, how can we optimize it? So thank you everyone, and see you later.